You have just finished reviewing simplifying and solving, both standard and advanced. We're about to review solving simple inequalities in one variable, and for that we need set builder notation. In a minute we'll see why. Many inequalities fall into the category of what you see is what you get. Example 1 is like that. Take a look. First, I subtracted 3 from both sides. Then I divided by 6. I added 5 to both sides and divided by 2 and ended with x is less than 3. In Algebra 1, you made a graph that looked like this, with an open circle around 3 to show that it was less than but not equal to, and an arrow that went to the left to show that you wanted x's that were smaller than 3. This graph won't change in Algebra 2, it's just the way you describe it that will. Many inequalities come with a twist when you divide by a negative and reverse the inequality. Example 2 is like that. Take a look. I started by subtracting 3 from both sides, but instead of dividing by 6 this time I decided to distribute it. That gave me negative 12x plus 30 is less than or equal to 6. I subtracted 30 from both sides and then divided by negative 12 and got x is bigger than or equal to 2. The reason I said that it had a twist is because it started out less than and ended up greater than when I divided by the negative 12. The graph again looks like this, with a filled-in circle at 2 to show that equals 2 is now included, and an arrow that went to the right to show that I wanted x's that were bigger than 2. In neither example, however, did I box in the inequality that I had found by doing algebra. That is something you did in Algebra 1, but in Algebra 2 we need to be a little more sophisticated. The graphs I provided, you know, the ones you said wow when you saw and admired so much, had all real numbers shaded in. It's common practice for solutions to inequalities to include all real numbers. The truth, however, is that problems are solved for all sorts of situations, and in some of those situations, not just any real number can be a solution. If x is the number of students at a particular school, x cannot be a decimal or a fraction, and it can't be negative either, no matter how bad a day you're having. When describing the solution to an inequality, we need to be specific and say which set of numbers we're using in the particular example we're working on. Each has a name and an abbreviation. Capital N stands for natural numbers, which are 1, 2, 3, 4, sometimes called the counting numbers, and they do not include 0 or negatives or fractions or decimals. The whole numbers are the same as the natural numbers as long as you add in 0. The integers are positive and negative. The rational numbers are fractions, which is why they're called Q for quotient. Quotient is the answer to a division problem. All the fractions, positive and negative, are rational. And finally, we get to the real numbers, which include all the fractions, positive and negative, and all the decimals that are fractions and the decimals that aren't. In example 1, you saw this, and x came out to be less than 3, and the graph looked like this. In example 2, you ended up with x is bigger than or equal to 2, and a graph that looked like this. How can we write a solution set in Algebra 2 that reflects the fact that we're allowed to use all real numbers? Here it is, and it's called set builder notation. I worked on it in color so that you could see what went with what. When you start set builder notation by putting set brackets on either side. I drew them in red, and when you see them you say the set of. Then I chose x as the variable for my set description because x was the variable that we used in the equation. The truth of the matter is I could use any letter I want, although the letter usually is the same letter, or variable, I should be fancy here, that you use in your original problem. Then this little symbol over here stands for that are, and this means real numbers. So this is the set that contains numbers that are real. This bar says that I'm about to provide you with additional information about your set. And after the bar, I put x is less than 3. You'll notice over here that I gave you a little background that this symbol is the Greek letter epsilon and it's the Greek letter E, and the reason for that is because originally when set theory was first created. They call the numbers or the things in the sets elements. Element starts with E, and so epsilon really means is an element of or belongs to. The description bar lets you know that you are about to find out some special rules that the numbers in the set must obey. And I know that's a strange concept nowadays. Obeying means doing what you're told. It is something that numbers still have to do, and students sometimes don't. Sometimes instead of the bar, you'll see a colon, although the bar is the most popular one in high school and college. In example 2, you see the same set builder notation with the same set brackets on either side, the same XER to show you that the numbers are real numbers, the description bar, and now the condition that X has to be bigger than or equal to 2. Another popular form of writing solution sets, which is more college than high school, although you will sometimes see them in high school books, is called interval notation. It describes what you see when you look at the graph. So this graph starts at negative infinity, so to speak, and goes until 3 and stops. So our interval notation starts with negative infinity and ends with 3, and the rounded bracket means that 3 is not included. This graph, however, which starts at 2 and goes to positive infinity, is written with the notation 2 comma infinity, and you'll notice that the 2 is boxed off instead of round because 2 is included. The infinities all have rounded brackets because you can never arrive at negative infinity or positive infinity. Negative infinity is this arrow, positive infinity is this arrow. They are locations you can try to reach, but you never actually arrive there, at least not until you get to graduate school. See, I just gave you something to look forward to. From now on in Algebra 2, whenever you work on a problem that's an inequality and has an infinite solution, you're going to write your official solution set either using set builder notation or interval notation, whichever of the two you prefer. But going back to the olden days where you just said x is less than 3 or x is bigger than or equal to 2, those days are gone, so say bye-bye.